Okay, yeah. So the Beer-Lambert law is this relationship between the absorbance of a solution and the concentration of that solution. So you know how when you make Kool-Aid, you can kind of tell how strong it is based on what color it is.
Yeah.
Okay, that's what this is about. Except we're going to use a machine called a Spectroviz Plus, which is a spectrophotometer, and it's going to measure the amount of light that's absorbed by uh, by a solution, and then we're going to use that to make a calibration curve, which is going to be these standards. So you plot this point, you plot this point, you plot this point, you plot this point. This should be a linear relationship once you plot all those points, and then you can do a line of best fit. And then if you have an unknown, so you don't know the concentration of it, but you can stick it into the spectrophotometer and measure the absorbance. So you measure the absorbance, use your line of best fit or your equation or whatever, and figure out what the concentration of that unknown is based on the absorbance that you measure from the machine. The way the machine works is you have this thing, this clear, yes, plastic thing called a cuvette, and you put your colored solution in that. So, like the one we're using, I think is like a pinkish purple color, the cobalt 2 chloride. And then inside of the machine, there's a light source. And that light is going to shine through the solution, and some of it's going to get absorbed. And then there's a detector over on the other side that measures how much light makes it through. Okay, how much would a clear solution absorb, or what would you expect, or how? Yeah, I phrased it right the first time. Okay, how much would you expect a clear solution to absorb light that goes through it? Not much. So you would expect the absorbance to go from zero, being like completely clear, pure water, and then the deeply colored solution, you want your absorbance to max out somewhere 1.0, 1.1, 1.2, something like that. I'll go here. So if you go more concentrated or more deeply colored than that, you just won't be able to get a good linear relation. Like if you go beyond it, eventually this thing starts to curve and the absorbance levels off because it's just absorbing all the light that's going through the solution. Now, the equation here is the absorbance equals the absorptivity, which is a property unique to each solution or each solute, times the path length times the concentration. Now, when we do experiments with this, absorptivity and path length are going to be constant. The path length is how much colored solution the light actually has to travel through. So those cuvettes, I think they're like a 1 centimeter path length on all of them. So that'll be a constant. The absorptivity, we're going to use the same compound all the way through, like we're going to use cobalt 2 chloride. So the only thing that's actually a variable is the concentration. So when you think about this, you can think about it kind of like a y equals mx thing, except, and then b should be zero. The intercept should be zero here. So the concentration is like your x quantity, and your absorbance is the y quantity you're going to measure, and then the m, the slope, is the path or the absorptivity times the path length. So we're going to use a linear line of best fit to model these different concentrations. And the challenge for you will be making the different concentration solutions and then measuring the absorbance and then doing the line of best fit. And then you'll have an unknown and you'll have to measure the absorbance and then figure out what the concentration is. And past students have done pretty well with this. Okay. Any questions about that? Okay. Do you feel like you know something more about this than you did before? Okay. Yeah. All right. And it's a really simple concept that you can observe on, in your daily life, but we're going to take it and use it to do something. And spectroscopy is a very frequently used technique for determining the concentration of things in chemistry, just in chemistry in general. Actually, let me go back up here and do one more thing. So if you go across a spectrum of visible light, so let's say that we go from like 300 nanometers, which is actually a little bit outside of visible light. That's getting into UV. And let's say we go up to like, I'll just go to 700, which is like red light. Yeah, 400 is like blue. Okay, so if you do a plot like this for the cobalt-2 chloride, and I don't remember what it looks like, but let's just say that you do the plot and it looks like this. Okay, what's probably going to be like your ideal wavelength to use? Yeah, whatever the peak of this absorbance versus wavelength graph, that's a pretty good place. Or really anywhere, I guess within like 90% of the peak or something like that. So if I recall correctly, that lab has you do this kind of thing first, identify which wavelength is best, then set up to measure at that particular wavelength when you're doing this absorbance versus concentration graph. So you do need to, it doesn't matter which wavelength you pick to use. And generally, you're going to pick the maximum there. Okay, let's see. So talking about different types of spectroscopy, just for your information, the different transitions are related to different things. So ultraviolet and UV is going to be associated with energy level transitions. So like, you remember the Bohr model stuff where you have like the different rings and maybe the electron transfers from here to this higher energy level. Okay, that's going to be something that's usually in the visible or UV range of energy. So you would have to put visible or UV in to get it to jump up, and then when it relaxed back down, it would give off that wavelength, whatever it is, somewhere in the visible or the UV range. Get it as you get higher up into the UV range. Sometimes UV radiation is actually enough to cause an electron to just completely be ejected from the atom. And then X-rays and gamma rays beyond that certainly have enough energy that they would cause electrons just to be like, X-rays usually are going to cause the electrons just to be ejected from the atom, not to move up to a higher energy level. The infrared radiation is related more to temperature and vibrations in the molecules. So that can be more related to like what type of bonding is going on inside of the molecules that you're interested in. And I remember, I think it was organic chemistry. We did a good bit of IR spectroscopy with that, trying to figure out stuff about the structure of organic molecules. And I remember that being interesting and really maybe complicated kind of at the same time. All right. So let's move on and dig into some problems here. Yeah. Yeah. So I don't know if I'll get through all of these today. I feel like we may end up going a little bit over on time today, so we may not get to lab as much tomorrow as I would like to, but we'll see.